Let's now consider martingale valuation. We begin with a familiar definition, namely that of arbitrage. As in discrete time, an arbitrage strategy is a self-financing trading strategy phi with the following properties. Its initial value is zero, in other words, initially it costs nothing. The probability that its terminal value is greater or equal to zero is 1, in other words, there is zero probability of a loss. And finally, the probability that its terminal value is strictly greater than zero is strictly greater than zero. In other words, there is a strictly positive probability of making a profit. As we've seen, you can regard an arbitrage as a free lottery ticket. It costs nothing, there is no chance of a loss and some chance of winning. And as usual, we will make the assumption that there are no arbitrage strategies, i.e. no free lottery tickets. And this is because if there had been any, I would have taken them all. Now we extend our definition of an equivalent martingale measure slightly to include other numeraires. Suppose that n is a numeraire, which, if you recall, is the price process of a non-dividend paying asset with strictly positive value. A measure q hat on a measurable space omega f is called an equivalent local martingale measure, EMM, for a numeraire n, if and only if q hat is equivalent to p, and the numeraire deflated asset prices S hat, i.e. S divided by the numeraire n, is a local q hat martingale. An equivalent martingale measure associated with a bank account is called a risk-neutral measure and denoted by q. In other words, a risk-neutral measure specifically refers to a measure under which discounted asset prices are martingales, and by discounting we mean discounting by the bank account. But we've now introduced the notion of an equivalent martingale measure also for other numeraires, which need not be the bank account. Now observe that if q hat is an equivalent martingale measure for numeraire n, then the deflated value process v hat and gains process g hat are both q hat martingales. This is essentially because v hat is a stochastic integral with respect to s hat, and s hat is a q hat martingale. In other words, v hat is a stochastic integral with respect to a martingale and therefore a martingale. As in discrete time, we have the following theorem. If an EMM q hat exists for some numeraire n, then there are no arbitrage opportunities. Let's have a look at the proof. Suppose that q hat is an equivalent martingale measure for numeraire n, and that phi be a portfolio that satisfies two of the properties of an arbitrage, namely that its initial value is zero, and that the probability that its terminal value is non-negative is equal to 1. In other words, that there is no chance of making a loss. Since the measure q hat is equivalent to the measure p, it's also the case that under q hat, the terminal value of the portfolio is non-negative with probability 1. Now by the martingale property, the q hat expectation of v hat at time capital T is equal to v hat at time 0. Since we assume that the initial value of the portfolio is 0, we see that v hat at time capital T is a non-negative random variable with 0 q hat expectation, and therefore v hat t is equal to 0 q hat almost surely. Again, because q hat is equivalent to p, it must be the case that v hat at time capital T is equal to 0 p almost surely as well. And hence phi cannot satisfy the third requirement of an arbitrage, namely that there is some chance of making a profit. In other words, any portfolio that satisfies the first two properties of an arbitrage cannot satisfy the third, and hence there are no arbitrages. As in discrete time, we also have the following result. Suppose that x is an attainable contingent claim, and that q hat is an equivalent martingale measure for numeraire n. Then the numeraire deflated price of the contingent claim x is a q hat martingale. In other words, the time t value of x is the time t value of the numeraire times the conditional expectation of the numeraire deflated payoff. The proof is the same as in discrete time. Suppose that phi is a replicating portfolio for x, in other words that the terminal value of the portfolio phi is equal to the payoff of x. Then by the law of one price, the value of the derivative is equal to the value of the portfolio for any time before the payoff. In particular, x hat is equal to v hat t. By the martingale property of v hat, We obtain the following. And then since phi is a replicating portfolio, this random variable inside the conditional expectation here is equal to the numeraire deflated payoff. If we compare the first term with the last term, we obtain the result. We now look at the setup for the generalized Black-Scholes model. Here we will work in a probability space omega fp, which will be equipped with a k-dimensional standard p-Brownian motion, W, which has capital K many components. And that Brownian motion generates the filtration F, which is augmented to satisfy the usual conditions. We assume that there are capital N many risky assets whose price processes S form ether diffusions with the dynamics of the following form. Here both the coefficients mu n and sigma nk are allowed to be stochastic processes and assumed to be such so that their respective integrals, a Lebesgue integral here and a stochastic integral here, all exist. We have here capital N many stochastic differential equations, which we can write as a vector equation as follows, which can then be abbreviated like this, where dst over here is the diagonal matrix with the asset prices along the diagonal. The vector mu is called the drift vector, and the matrix sigma is called the volatility matrix. Both of these can be stochastic processes. We also have a bank account, S0, which we will also denote by A, which has dynamics dAt is equal to RT AT dt, where R is the short rate and may be stochastic as well. As usual, we assume that the initial value of the bank account is 1, and for the next few slides, the bank account will serve as numeraire. Let's just quickly review Gersanov's theorem for Brownian motion. Suppose that we have an n-dimensional process with the following dynamics, where W is a d-dimensional Brownian motion. Let lambda, also d-dimensional, be a predictable process, the so-called Gersanov kernel, and define a new measure Q on the terminal sigma algebra F capital T as follows. The Q by dp is the Dolian exponential of the stochastic integral of the process lambda with respect to the Brownian motion W, evaluated at the terminal time t. Assuming that no Wyckoff's condition holds, then we see that Q will be a probability measure on the terminal sigma algebra. We obtain a Q Brownian motion from the original Brownian motion by subtracting the integral of the Gersanov kernel, in which case it is easy to see that the Q dynamics of Y are modified as follows. The drift is changed, we add the volatility of Y times the Gersanov kernel to the drift, and the volatility process remains unchanged. Let's use Gersanov's theorem now to construct a risk-neutral measure. Here we will work with a finite time period from 0 to capital T in the generalized Black-Scholes setup that we just discussed. As an exercise, you can apply Ito's formula to obtain the dynamics of the discounted asset prices. The p-dynamics of the discounted asset prices are then given as follows. Here d bar st is the diagonal matrix with the discounted asset prices along the diagonal, and the vector 1 here is a constant vector with 1s in every component, which is capital N dimensional. If we effect a Gersanov transformation with k-dimensional kernel Xi, so that dq by dp is the Dolian's exponential of the stochastic integral of Xi with respect to W evaluated at the terminal time, then the Q dynamics of S bar will be modified. We will change the drift by adding the volatility times the Gersanov kernel to it. The volatility component will remain unchanged. Now, to ensure that the discounted asset prices are Q martingales, we must make the drift disappear. In other words, it must be the case that this term here, mu t minus rt1 plus sigma t xi t, is equal to 0. Remember that a risk-neutral measure is a measure under which the discounted asset prices are martingales, i.e. driftless, and therefore in order to construct a risk-neutral measure we must make sure that we find a Gersanov kernel Xi which satisfies this equation, which we can rearrange to obtain the following equation. The unknowns here are the entries of Xi. This is a linear system. In other words, what we have here is capital N linear equations in capital K many unknowns for each t and each sample point omega. The unknowns are the entries of the vector Xi. Before we proceed now, let's have a look at a little linear algebra, a version of Farkas' lemma. Recall the following facts. Suppose that X is a linear subspace of R to the d. Define X perp to be the collection of all vectors in R to the d which are perpendicular to every vector in the subspace X. In other words, X perp consists of all y in R to the d such that y is orthogonal to the subspace X. In that case, it's easy to see that X perp is also a linear subspace of R to the d, and moreover that the dimension of X perp is a complement of the dimension of X, i.e. the dimension of X plus the dimension of X perp is equal to d. It's also easy to see that X is contained in X double perp, in other words the orthogonal complement of X perp. For if X belongs to the subspace X, then every vector in X perp is orthogonal to X, so X is also orthogonal to every vector in X perp, which is the same as saying that X belongs to X double perp. Moreover, using this equation here, we see that X and X double perp have the same finite dimension, in other words X is equal to X double perp. Finally, if X and Y are subspaces of R to the d, and if X is contained in Y, then it is also easy to see that Y perp is contained in X perp. For if a vector belongs to Y perp, then it is orthogonal to every vector in Y, hence it is orthogonal to every vector in X, because X is contained in Y, and hence that vector belongs to X perp. In other words, any vector that belongs to Y perp belongs to X perp. Let's now state Farkas' lemma. Let B be a d-dimensional vector and let A be a d by n matrix. If for every d-dimensional vector X it is the case that X transpose times B is equal to 0 whenever X transpose times A is the 0 vector, in other words, if it is the case that whenever the dot product of X with B is equal to 0, then the dot product of X with every column of A is 0 also, then there is a vector Y in R to the n such that B is equal to A times Y. Here's the proof. Denote the columns of the matrix A by the vectors A1 up to AN. To say that X transpose times B is equal to 0 is to say that the dot product of X with B is equal to 0. In other words, that X is orthogonal to B. To say that X transpose times A is equal to the 0 vector is to say that X is orthogonal to each of the columns of A. Thus, to say that X transpose times B is equal to 0 whenever X transpose times A is equal to 0 is to assert that every vector which is orthogonal to the column space of A is also orthogonal to B, and thus that every vector in the orthogonal complement of the span of the vectors AN is also an element of the orthogonal complement of the span of B. Now here we see that if X is contained in Y, then the orthogonal complement of Y is contained in the orthogonal complement of X. And thus the orthogonal complement of the orthogonal complement of B is contained in the orthogonal complement of the orthogonal complement of the span of the vectors A. Here we see that the orthogonal complement of the orthogonal complement is just the original. Hence we've shown that the span of B is contained in the span of the vectors A. In particular, the vector B belongs to the span of the vectors A, and thus the vector B can be written as a linear combination of the vectors A. In other words, there exists some constants y1 up to yn, such that B is a linear combination of the vectors A with coefficients equal to the y's. This is just the same as saying that the matrix A times the vector y is equal to the vector B. Let's now consider a little lemma that is a consequence of no arbitrage and will be useful in the construction of a risk-neutral measure. It asserts the following. If no arbitrage holds, And if theta t is a trading strategy of risky securities with the property that this expression here is equal to the zero vector almost surely with respect to the product measure consisting of the product of the probability measure and the Lebesgue measure, then it also follows that this expression here is zero almost everywhere. Here, sigma t is the volatility matrix of the vector of underlying assets, and mu is its drift vector. R is the riskless rate, as usual. Suppose now that theta t is such a trading strategy. Construct a trading strategy phi t, whose risky asset component is theta t times the indicator of the set where this expression is strictly greater than zero. Then adjust the bank account to make the portfolio self-financing with initial value 0. If we then consider the discounted terminal value of this portfolio phi that we've just created, in other words, this expression here, because its initial value is 0, and we substitute the value of the S bar in it, then we obtain the following. Now, by assumption, this expression here is 0, so the stochastic integral disappears. Hence, we're only left with the Lebesgue integral. And if we consider the integrand here, we see that it is non-negative. That's because we only consider the integrand here in the set where the integrand is non-negative. Since the integrand is non-negative, the integral is non-negative. In other words, the terminal value of the portfolio is greater or equal to 0 almost surely. Now, if the set over which we are integrating in that Lebesgue integral has strictly positive measure with respect to the product measure, then in fact the terminal discounted value of the portfolio phi would be strictly positive with positive probability, contradicting no arbitrage. In the same way, but using instead the negative of the portfolio that we used before, we obtain a contradiction if this set here has positive measure with respect to the product measure. Thus, both this set here and this set here must have measure 0 with respect to the product measure. In other words, this set here is a null set. From there, it follows that this expression here is 0 almost everywhere with respect to the product measure. That concludes the proof of the lemma. Now let's apply Farkas' lemma with the matrix A equal to the diagonal of S bar times the volatility matrix and the vector B equal to the diagonal of S bar times the drift of S bar. In that case, we see that whenever theta transpose times A is equal to 0, then also theta transpose times B is equal to 0. It therefore follows that there is a vector lambda such that A times lambda is equal to B. In other words, that this expression here is true. Since the diagonal matrix is invertible, we can cancel it on both sides, leaving this expression here. The volatility matrix sigma times the vector lambda is equal to the drift vector mu minus the riskless rate. We have omitted some technicalities about the measurability of the process lambda here. The process lambda is called the market price of risk or the risk premium. Let's quickly see where the name risk premium or market price of risk comes from. Consider first a model with only one source of noise, in other words a system where the assets are driven by a single one-dimensional Brownian motion. In that case, lambda is one-dimensional also. Then we can solve the system sigma times lambda is equal to mu minus r if and only if lambda is equal to mu n minus r over sigma n for all n. Here mu n is the drift of the nth asset and sigma n is its volatility. Now the numerator is the excess expected return above the riskless rate. And we are dividing the excess return by the volatility. In other words, lambda is the excess rate of return above the riskless rate per unit of volatility. In general, it would be a very bad idea to use just a single one-dimensional Brownian motion to drive many assets because then they would be super correlated. So if there is more than one source of noise, each source of noise can be ascribed its own market price of risk. The market price of risk of the kth source of noise, in other words the kth component of the multi-dimensional Brownian motion that we're using, is simply the kth component lambda k of the vector lambda. To see this, note that if we write out the nth row of the matrix equation sigma times lambda is equal to mu minus r, we obtain the following. And if we then change the kth component of the volatility vector of the nth asset by a small amount epsilon, then that will result in a small change lambda k times epsilon in the excess rate of return. And hence lambda k can be regarded as the excess rate of return caused by a unit change in the volatility corresponding to the kth source of noise. Now let's get back to the business of constructing a risk-neutral measure. First, recall that to construct a risk-neutral measure Q, we have to solve this equation here for Xi. In that case, a Kirsanov transformation whose kernel is Xi will remove the drift of the discounted underlying assets. In other words, we can construct the risk-neutral measure Q from the objective measure P via Kirsanov transformation whose kernel is Xi. But if no arbitrage holds, we can solve this equation. We've just seen, using Farkas' lemma, that no arbitrage implies the existence of a market price of risk. In other words, a vector process lambda satisfying this equation here. If we then take Xi to be the negative of lambda, it will satisfy the equation at the top. In other words, if no arbitrage holds, then we can construct Q from P using a Kirsanov transformation whose kernel is the negative of the market price of risk. Let's consider an example to make these ideas clear. Consider a Black-Scholes type model with two risky assets, only one source of noise, and constant coefficients, as shown here. Here W is a one-dimensional Brownian motion. To find a risk-neutral measure, we seek a Kirsanov kernel Xi, which will also be one-dimensional, which must solve the following equation here. And it is clear that a solution will only exist if mu1 minus r over sigma 1 is equal to mu2 minus r over sigma 2. In other words, if the market price of risk of the first asset is equal to the market price of risk of the second asset. Let's now look at the relationship between no arbitrage and the existence of an equivalent martingale measure. We have seen that the existence of an equivalent martingale measure implies no arbitrage. Further, we have seen that no arbitrage implies the existence of a market price of risk process lambda, which can then be used to construct an equivalent martingale measure for the bank account, in other words a risk-neutral measure, via Kirsanov transformation whose kernel is the negative of the market price of risk. We've therefore proved the following result. This is the fundamental theorem of asset pricing for the generalized Black-Scholes model. The generalized Black-Scholes model is arbitrage-free if and only if there is a risk-neutral measure. Now just some technical results about the existence of an equivalent martingale measure, which we just stated. To ensure that Q is a martingale measure rather than an equivalent local martingale measure, one has to ensure that the Doleans exponential of the integral of the negative market price of risk with respect to the Brownian motion is a proper martingale and not just a local martingale, for example using Novikov's condition. In more general models, where asset prices are driven by general semi-martingales rather than just ether diffusions, the no arbitrage condition is too weak to guarantee the existence of an equivalent local martingale measure. Instead, we say that the sequence of zero-cost trading strategies θn is an approximate arbitrage if their terminal values converges almost surely to a non-zero, non-negative random variable, and moreover for which the losses converge to zero uniformly in omega. This means that you can get as close to an arbitrage as you like. A model satisfies no free lunch with vanishing risk, i.e. NFLVR, if there are no approximate arbitrages. Delban and Schachermayer proved in a paper in 1994 that there exists an equivalent local martingale measure if and only if no free lunch with vanishing risk holds. Certain boundedness conditions on stock price processes are necessary to ensure that a given equivalent local martingale measure is actually an equivalent martingale measure.